Hello, this is a quick introduction to the Negabinaries, which is a base -2 representation for numbers. And I'm going to assume that you know what base means for representation for numbers. Normally we write base 10, and this is about base -2. It's interesting because it's negative. My name is Tyler, and I'll be presenting this. So just a really quick history of representing numbers. The oldest is probably what I'm calling unary notation, which is just counting, just writing one tick mark per item. And then Roman numerals is sort of advanced counting, where there's different letters for different units, but really you just repeating that letter to represent that many repetitions of the unit, basically. And then base 10 is what everybody uses today, so everybody knows about that. Base B generalizes that, and one of the most common is binary notation, base 2, which is what computers use, and we can also sort of use base 8 or base 16 with computers. You might also be familiar with, say, something sort of like base 60 for seconds and minutes, and sort of like base 12 or 24 for hours of a day. So normally in base B notation, you have a string of digits. So each of these a sub k through a sub 0 is a digit, and it basically is a polynomial where the variable of the polynomial is b, the base. And we always keep the digits between 0 and b minus 1, which is always going to be something analogous to 9. So every integer using this system, for positive b, it's very easy to see it has a unique representation. Okay, now here's some interesting ideas. What if the base is a negative number? What if the base is a complex number, or the digits aren't 0 through 9, or even the units are not powers in an integer? So the idea of a quarter imaginary base was presented by Donald Knuth in a high school talent search in 1955. And the idea is that use 2i, the number 2i, as your base, b. And it turns out that any Gaussian integer can be uniquely represented as a finite string. You don't need a negative sign anymore or the letter I. You just have everything's a finite string. And then with the radix point, you can actually get all the complex numbers. So that is very interesting. Balanced ternary notation plays with the idea that, okay, it's base 3, but instead of using the digit 2, we'll use the digit -1 instead. You still get unique representation of all integers, and a couple cool properties. Negation is swapping symbols, -1 and 1. You never need a negative sign, and if you truncate a string with a radix point, like a decimal point, then you're actually rounding to the nearest integer. Another idea is the Fibonacci base, which it gets rid of the idea of these exponents of your powers of your base as being sort of the coefficients of your string, and what you replace it by is exactly the Fibonacci sequence. This can be used, I actually don't know many applications. I think it can be useful for explaining Fibonacci heaps. And an interesting property is basically, it's not, if you have a 1-0 string, it's not necessarily a unique representation of an integer, but if you have the rule that you can never have two 1s in a row, then it becomes a unique representation for all the integers. Okay, Negabinary number line. So this is just the beginning. I'm just writing, on the right-hand column is all the length 2 strings. Sort of imagine there's prepended zeros for the top 2. And basically the values -2 through 1 can be represented by the strings 1, 0, 1, 1, 0, and then 1. And so that's just to get us started at looking at this. And what I'm going to do is I'm going to sort of show you a picture of the structure of the Negabinary number line. So if we start with one digit, we get 0 and 1. If we add a new digit, then we get the numbers -2 and -1, because that's the -2's place. And if I add another digit, so now it's a 3-length string that represents an integer, the interval is now -2 to 5, because we've added 4, that's -2 squared, to all of the previous integers. And I keep on building what I can represent with strings, 0, 1 strings, as a Negabinary representation. So length 4 strings give me -10 to 5. And here's a piece of the number line. It's infinite, but this is just sort of the beginning of it. Okay, that little star means this is independent. It's not really impressive, and probably it's a reproduction of previous work. Let's see, so every integer has a unique string in every possibly negative base, and this is a very simple proof. We recursively prove that all strings of length n denote all integers in a contiguous interval of length b to the n. And so it's very easy to recursively prove that. For n equals 1, it's trivial, and then at each step, what you're doing is you're adding a b to the n to every element in the previous interval. So what happens is, obviously, they don't overlap, and because b to the n plus a number in the contiguous interval has to be sort of, I'll say, touching or directly adjacent to that interval, we maintain that it's a contiguous interval. And you could formalize that. I'm just sort of going quickly because of the time limit. Okay, and so sort of just to show the picture of what's happening, this table, it's a little repetitive here, but I'm showing that the interval is growing, and it's always a continuous interval. So when the length of the string goes from 1 to 2, we go from 0, 1 interval to negative 2, 1. We add a new digit, and we go from negative 2, 1 to negative 2, 5. We add a fourth digit, and we go from negative 10. We go up to negative 10, comma 5 as our interval. And just here's another picture, same idea of how it's growing. Now, what I'm going to pull out of this picture is that there's always an interval that's sort of around 0, but 0 is not at the middle of it. It's actually always going to be offset by about 1/6 of the whole interval, and that we always have twice as many, roughly twice as many numbers on one side of 0 on the other. This is looking at all strings of a fixed length n. And one thing we can also get out of this is that all odd length strings are positive, and all even length strings are negative. Now, when I look at the length now, I'm assuming there's no leading zeros here. So if it's an even length, here's a quick explanation. That means the most significant digit is 2 to the a negative 2 to a even number, so it has to be a positive value, and that's going to be a larger positive value than the sum of all the negative values that might be less significant than that. Okay, how do you add a negabinary? You only really need the first two rules here, but the third rule will help you avoid infinite loops. For a computer, you might not worry about quote-unquote infinite loops because you're going to have probably fixed length precision, but I'm going to include the third rule because it makes things more fun. So the first rule basically says 1 plus 1 is equal to 2. That's how you write 2 in Negabinary. And then this is how you write 3 in Negabinary, and it's interesting that 1, 1 represents negative 1. So when 1, 1 plus 1 happens, it's actually cancel each other out and get 0. So we'll just do a really quick example of this. 1, 1 in the least sig column gives us 1, 1, 0. And then I'm going to get 1 plus 0 plus 0 is easily 1. And then in the next column, we'll have 3, so we're going to get a 1 and 2 1s in the carry. That's from the second rule. Now easily I have 1 in this column, and now I have another case of 2. But actually what I'm going to do is I'm going to notice, hey, this is a case of the special rule 1, 1 plus 1 equals 0. So those guys are going to cancel out, and my final answer will actually be shorter than the first summand, the first input. And if I want to kind of check my work, I can convert to decimal. The top number here in the sum is negative 11. It's plus 5, and the answer we get is negative 6. It works.